Okay, everyone, we're continuing our statistics practice test, and we've got number 6, which is a random variable x is normal with a mean of 55 and a standard deviation of 1.2. And then the random variable y is also normal with a mean of 20 and a standard deviation of 4.5. So for part A, we're supposed to find the means of x plus y and x minus y, and then the standard deviations of x plus y and x minus y. So the mean of x plus y is just the mean of x plus the mean of y, which is just 55 plus 20, or just 75. Similarly, the mean of x minus y is equal to the mean of x minus the mean of y, or 55 minus 20, or just 35. Standard deviations don't exactly play the same way. For a standard deviation, you have to find the variances first, add them, and then take the square root. So the standard deviation for x plus y is equal to the square root of the variance of x plus the variance of y. So that's the square root of 1.2 squared plus 4.5 squared, which is just 4.66. Now, the standard deviation for x minus y is a funny thing, because you would think that you would subtract the variances for x and y, but actually, you would add the variances. And the way I like to think about it is, if you're going to add two things with uncertainty, then your result is going to be more uncertain than what you started off with. In other words, by subtracting two random variables, we don't decrease the variation, we increase the variation. Variances always add, they never subtract. So if it's the same formula, well, we're going to get the same result, 4.66. Now part B says to find the probability that x plus y is greater than 70. So we'll start with that. Sorry, less than 70. And for this one, we're just going to shortcut our way around it with the calculator. Since we've already shown in the previous video, we've already shown us calculating the standard deviation with the probability with the z-score. So we want to know less than 70. We don't know if there's a floor for this, so we'll go to negative 1e99, which is basically negative infinity for this calculator. And we want to know less than 70. We know the mean is 75, and the standard deviation we calculated at 4.66. So that gives us a result of 0.1416. And as you can see on the paper, I've just kind of written all of the basically all of the work that we were supposed to do. We found the z-score of negative 1.073, and of course that probability is going to be the same. The next one we're going to do on our calculator is the probability that x minus y is between 32 and 42. Going back to my calculator, we'll do the distribution and normal CDF. In this case, my lower is 32, my upper is 42. The mean is going to be 35, and that standard deviation is going to stay the same. So that gives me 0.6736. You can see in our paper we're going to be writing out our two z-scores, negative 0.644 and 1.502. And we'll calculate the probability that x minus y is between 32 and 42. It's the same thing as the probability that a z-score is between negative 0.622 and 1.502. And finally, that same answer that we got from our calculator, 0.6736. This brings us to number 7. It's been estimated that about 30% of frozen chickens contain enough salmonella bacteria to cause illness if improperly cooked. A consumer purchases 12 frozen chickens, so what's the probability that the consumer will have more than 6 contaminated chicken? the first thing I invite you to do is to write down that the variable you're going to use, x, is a binomial variable, and have the mean and the standard and the probability of success. It's actually really important that you write this, because once you get to the AP test, if you start to use the binomial distribution without saying that something is a binomial, you will lose points. So we want to find out the probability that x is greater than 6. Now I try to make a habit of, you see that we have x is strictly greater than 6, but I make an effort to try and write this with a greater than or equal to sign. So we're talking about 7, 8, 9, 10, 11, or 12. And this is important because now when I have to write this as a complement, I know that 6 has to go with the complement of greater than or equal to 7. This is important because a lot of calculators won't calculate a binomial probability for x greater than or equal to, but they will do less than or equal to. So if I go to my calculator and I go to second distribution and I find my way to binomial CDF, okay, you'll notice that it's only going to calculate for x less than or equal to a certain number. So we know that this is a 12 and 0.3 binomial distribution, and we want to know less than or equal to 6. And that's going to give me this right here is the probability that x is less than or equal to 6. So for my problem, I need to do the complement of that. So 1 minus that. That's going to give me everything greater than or equal to 7. So 0, 3, 8, 6. So always try to think about, where less than or equal to, how does that work? So if we have greater than 6, that means the complement is less than or equal to 6. Next, we have a certain large population. 40% of the households have a total income of over 70,000. A simple random sample is taken of 4 households, and let x be the number of households with an annual income over 70,000. And assume that this is binomial assumptions are met. So what is the mean of x? So x is a binomial distribution with a n equal to 4 and p equal to 0.4. That $70,000 number, that's a number that really is just there to confuse you, or it's going to serve to confuse you, because you're only concerned about the sample size is 4, the probability of success is 0.4. And in a binomial distribution, the mean is just n multiplied by p, which is 4 multiplied by 0.4, or 1.6. For number 9, the probability that a widget machine will produce a defective widget is 0.0012. So how many widgets do you expect to examine before you discover a defective widget? And this is our first look at a geometric distribution, because most of the binomial distribution things conditions are met. I mean, we have either defective or not defective. We're kind of assuming that the probability of producing a defective widget is independent, or the defectiveness is independent, I should say. We're interested in how many trials before we discover the first defective widget, and the same probability of success, or I guess defectiveness in this case, is 0.0012 for each widget. Now the mean of a geometric distribution is 1 over p, which basically tells you how many will you expect before the first success. The first success should happen around 1 over p, which in our case is going to be 1 divided by 0.0012, or around 833.33. Now the last thing for this video is number 10, where a binomial distribution has n equals 120 and p equals 0.22. and we're supposed to use a normal approximation to estimate the probability that x is between 30 and 60. The first thing we need is a mean, and the mean is n times p, which is 120 multiplied by 0.22, or just 26.4. The next thing we need is a standard deviation, which is the square root of np multiplied by 1 minus p, which is going to be 120 multiplied by 0.22 multiplied by 0.78, which is 4.54. We're going to calculate our two z-scores here. So the first z-score is x minus mean over standard deviation, which is 30 minus 26.4 over 4.54. That's equal to 0.793. And then we'll calculate z2 pretty much the exact same way. X minus mean over standard deviation. So 60 minus 26.4 over 4.54. Or 7.40, which is a really big z-score. Next, we can set up our probability statement. We've got the probability that x is between 30 and 60. That's equal to the probability that a z-score is between 0.793 and 7.4. And we're ready for our calculator. Back at our calculator, we're going to go to our distribution and normal CDF. Now you could use the z-scores, or you can use everything in terms of x. I'm going to do everything in terms of x. And 30 to 60, the mean was 26.4, and the standard deviation was 4.54. And that gives me 2139. Write that in, and you're ready, all set. All right, all that's left are those 3 free response questions, and we'll be looking at those in the next video. Have a good one, everyone.